Good afternoon, and thank you for joining us for our special guest webinar, Model-Based Systems Engineering Demystified. My name is Elizabeth Steiner, and I'll be the moderator for this webinar. Today, you'll be hearing from our guest host, Dr. Warren Vanneman. But first, let's go over some quick housekeeping. During the presentation, feel free to send us questions using the panel on the right. We will get those questions answered in the question and answer part of the webinar. You can also interact with us on LinkedIn through the Innislate user group or through Twitter using the handle @Innislate. The webinar is being recorded and we'll make it available to you after the live presentation. So please be sure to keep an eye out for it in your inbox. Now I'd like to introduce you to our presenter, Dr. Warren Vanneman. He'll be adding clarity to the ambiguous concept of MBSE and discussing the intent of moving the subdiscipline forward. Dr. Warren Vanneman is the Professor of Practice in the Systems Engineering Department at the Naval Postgraduate School in Monterey, California. He has more than 30 years of leadership and technical positions within the U.S. Navy and the intelligence community. Dr. Vanneman has been conducting research in MBSE for unmanned systems, enterprise systems, and systems assistance since July 2011. To enhance his research efforts, Dr. Vanneman teaches several courses in systems engineering and architecting and systems of systems engineering and integration. Prior to joining NPS, Dr. Vanneman has held various systems engineering positions within the intelligence community, including Chief Architecture Analysis Division and Chief Architect of the Enterprise Ground Architecture at the National Reconnaissance Office, and Lead Systems Engineer for Modeling and Simulation at the National Geospatial Intelligence Agency. Dr. Vanneman is also a retired captain in the Navy Reserve, where he was qualified as a surface warfare officer, space cadre expert, and information dominance warfare officer. He had the pleasure of serving in 6 command tours, including a command tour in Afghanistan. He has a BS from the State University of Newark Maritime College, a MS in Systems Engineering, and a PhD in Industrial and Systems Engineering from Virginia Tech, and a Joint Professional Military Education Phase 1 certificate from the Naval War College. I'll go ahead and hand over controls to Dr. Warren, and we'll go ahead and get started.
Okay, so thank you, Elizabeth, for that kind introduction. Thanks to you and Steve for inviting me to be the guest speaker today. So it's quite an honor and privilege to be here for this group. So and thank you for those who are joining the webinar, that you're taking the time out of your day to care enough to come to hear my presentation. So first, as Elizabeth said, I am from the Naval Postgraduate School. Maybe some of you haven't heard about the Naval Postgraduate School, but the schoolhouse is actually in Monterey, California. I should say beautiful Monterey, California. I don't live there. I actually live in Virginia. I do a lot of distance learning classes. So what we do at the Naval Postgraduate School is we believe that we provide a unique education to our students, both military and DoD civilian, and we help them provide this. We provide this unique education because we come from a different perspective. We come from a Navy perspective. We're not Virginia Tech or University of Maryland, and I'm not trashing any of those schools, but from a Navy perspective, the students come to us. A lot of us have clearances. We're able to work on projects and research that are relevant to the field. So that's a commercial. NPS is a world-class institution. The systems engineering program there is ranked 20th according to U.S. News and World Report. So it's actually a good place to be. So for those of you who don't know anything about Naval Postgraduate School, now you do a little bit, right? So I wasn't here to talk about Naval Postgraduate School. I was here more talk about model-based system engineering. And this presentation actually originated with because I was frustrated. Everywhere I go, it's I hear something else from about model-based system engineering, right? So that's why I called it model-based system engineering demystified. I was trying to get my arms around, okay, what is really model-based system engineering? So you'll see model-based system engineering from my perspective, I guess. Probably not my perspective. I know there's others online that probably agree with me. So some people, when they talk about model-based system engineering, they I hear Warren, model-based system engineering is equal to Sysml, or model-based system engineering is equal to UML, or model-based system engineering is equal to LML. And in fact, those are just modeling languages. They're part of model-based system engineering, but they're really modeling languages. Okay, and then some people say, well, model-based system engineering is equal to Department of Defense architecture framework or the unified architecture framework. And so, you know, those in my vernacular aren't really model-based system engineering. It's total. They're really called presentation. Those are usually presentation frameworks. No, I can't. It's not advanced. You know. Okay, a little bit of technical difficulties. There we go. So it's fixed. And then some people say, you know, I hear this a lot. I hear model-based system engineering is equal to magic draw. Model-based system engineering is equal to InnoSlate. Model-based system engineering is equal to core, right? And I don't believe that those to be true either. I believe those are really modeling tools that allow us to do model-based system engineering. So the goal of this presentation is to get you to think a little bit differently about model-based system engineering. If you believe model-based system engineering is any one of those by itself, hopefully I'm going to get you to think a little bit differently about model-based system engineering in this presentation. So let's look at the state of system engineering. So our systems are becoming larger. Our systems are becoming more complex. There has to be a way to deal with that complexity. And unfortunately, at this point, the system engineering community is not keeping pace with the complexity of systems, or at least being able to design the complexity of systems. You know, I was in one presentation the other day, and the guest I was a guest in somebody else's class. I was able to attend this guest presentation that they had, and the presenter basically threw up his hands and said, you know, this stuff is too hard. And so really was questioning, well, why are we doing this since it's really hard? Well, that's an interesting question, but you know, the topic of complexity and the problems that we're being faced with and trying to address are not going away. Yeah, okay, so maybe we're not addressing them very well at this point, but we have to continue to make progress into being able to address them. And I believe model-based system engineering is a way of trying to address the complexity. And I think as the tools become more sophisticated and we actually figure out where we're going with model-based system engineering, then we'll be able to catch up and hopefully be able to manage that complexity. So let's look at a system. So forget about systems engineering as a whole, but you know, and the different documentation that goes along with it and all that stuff. Let's just look at what a system engineering project is. So this consider this cube here a system. If I look at that part of that cube, it provides some sort of width. And in system engineering terms, that width is insight across the entire system lifecycle. As you know, systems engineering is a lifecycle discipline. We have to have that visibility across the entire lifecycle. So that's one thing that's involved with this cube. It does have a lifecycle. Another thing this cube has, it has some sort of depth, right? I could provide a decomposition of different subsystems, assemblies, subassemblies, components all the way down to the part level if I wanted to within that cube. The cube is, as it's shown, it's really a black box, or maybe now a yellow and green box, right? But it's really a black box, and it has other it can be decomposed further. And within that system, there's some sort of relationships, right? That system performs some sort of function, right? And I can represent that system from its functional perspective. There's some sort of physical perspective. There's certainly the system perspective. There's requirements perspective, risk perspective, cost perspective, and that's all part of that. So when you think about model-based system engineering, maybe this is a good place to start. And hey, what are we really trying to address? We're really trying to address the system engineering project. Forget about what you've already learned about other things such as the different documentation. So when you look at model-based system engineering today, right? Model-based system engineering was conceived like 15 years ago, maybe a little bit more. Probably don't. I'm not a historian, so probably don't have that exactly right. But really, the vision of that was to transform these this paper-based world that we live in as systems engineers to more of a model-based process. So that was really the vision, to transform our discipline to that model-based, to a more model-based discipline. I argue today the way model-based system engineering is being implemented across, okay, so I'll limit my knowledge to, say, the Navy, maybe even broader terms, DoD. It's often being implemented, or for the most part, it's being implemented as I'm going to put something in, I'm going to put these paper products that I once have to generate in a sophisticated tool, and I'm going to signal touchdown, and I'm going to call it model-based system engineering. So what's really different between model-based system engineering and traditional system engineering? So as engineers of any flavor, what do? We use models. We use models, and those models could be in traditional system engineering. They could be drawings, they could be diagrams, they could be text-based descriptions like a ConOps document or an interface control document. From a model-based perspective, we really want the data maintained as a single representation. I'll talk about this in a little bit. But with that, there has to be some sort of common conceptual data model, some sort of common language. Hopefully, we're talking about having things in a single environment. I didn't say a single location. I didn't say single server. I said single environment. That single environment, some people, if you look at the DoD digital engineering strategy, they talk about the single source of truth, right? Or if you listen to someplace in the Navy, they talk about the single source of technical truth. It's not saying everything has to be located in one place, but everything has to be accessible to something else. The model has to be integrated, whether you use one tool or another tool to build this model, and it has to exhibit some sort of concordance. We'll talk about that in a little bit. So when I started this, one of the problems that we have is from a model-based system engineering perspective, there's a couple definitions out there. Okay, there's certainly a definition from NCOSE. They have their definition of, but when I look at the NCOSE definition, I guess I scratch my head and I want more, right? I can't tell how to implement it. I can't tell even what it is. What does it really look like? What are the elements of it? And other definitions that I've read, it doesn't break things down to the different elements. And basically, those definitions that are out there allows organizations to buy a tool such as Magic Draw, for example, and train their folks on their employees on Sysml, and then they go up and they are essentially putting things in a diagram format using a Sysml as the base, and they're putting in this fancy tool, right? And they're calling that model-based system engineering. So based on that, I looked around, I said, what are really the elements of model-based systems engineering? And I said, okay, well, so, and because the definition of model-based system engineering has really left me empty, I came up with my own, right? So here's my definition of it. It's now been published in a couple of papers, and as of the beginning of August in a book. I consider that the model-based system engineering is the formalized application of modeling, both static and dynamic, across the entire life cycle of the system. So what does that mean? I think it has model-based system engineering has 4 tenets. It has modeling languages, which Sysml, L UML, UML are part of that. It has some sort of structure to it. We'll talk about that in a little bit. It has some sort of processes. And then you have to be able to display that information that you're modeling. So decision makers can use it to actually look at the different alternatives and hopefully select the best alternative. And I call that the presentation framework. There's a couple tenets of model, jumping ahead, sorry about that. So when we look at the model-based system engineering environment today, so what happens today? We have some sort of model-based processes, and what's shown there is the DoD 6-step architecture process. It's generic. It's purposely generic. They kept it generic to so they're not going to tell you how to do the processes. You can use whatever process you want. You can use architecture process. You can use different system engineering process. You can use different analysis process. I don't care, right? But what happens is we have our favorite processes, and what do? We come over here on to all the way to the right, and we develop these things that look like these documents that we have always produced, right? And we produce those, and we do it in some sort of tool using some sort of modern language, and we often forget about or neglect, maybe just ignore structure. From a model-based system engineering environment, you have the processes. Use the tool to model your system, or the language to model your system, and you also develop some sort of structure where you're building relationships between the different entities within your system. And in the end, what you're able to do, you're able to output these documents that you're calling the presentation framework. The documents there, our senior decision makers are not going to let us get away from those documents, because that's kind of what they want to see. It helps them to do the analysis, or at least see the analysis that we've done, and it puts things in concise form without having them go into the actual tool or learn a specific language if your diagrams are language specific. So instead of going from the left side to the right side, then back to the center, we're taking a sequential approach from the left to the right. So, my mind, if you're going to have a true model-based system engineering environment, you have to represent the system as many times as it's represented in the real world, just once. So today, what happens? Today, even though we're using Sysml or some other modern language, what often happens? We come up with these diagrams, and then we have to correlate these diagrams ourselves, right? So the system could be represented any number of times. So you think about a requirements document, right? Or a series of requirements document. How many times is that same element within that system represented in the various requirements documents that may be in your requirements document hierarchy? And the answer is probably plenty, right? In fact, if you look at some larger programs like I have been involved with, what we used to have to do if we were going to change a requirement, we would have to do an analysis of all the documents, and we had to figure out how each requirement impacted other things within that system, right? And we have to do some sort of analysis and go present it to the bosses for them to say, hey, this actually makes sense. So in a model-based system engineering world, everything's represented one time. To help us do that, we say that we follow the principle of concordance. And the concordance is the ability to represent a single entity such that data in one viewer level of abstraction matches the data in another viewer level of abstraction when talking about the same thing. So what am I talking about, right? So think about this right here. Some of you may recognize it as a Navy F-18. Okay, so if I'm an operator, right? If I'm the operator, this is the perspective that I'm taking, right? I'm seeing that. If I'm the planner, that's what I'm seeing, right? I'm seeing something like that. If I'm the person who designed this F-18, or I'm the person who maintained that F-18, I'm going to probably view the F-18 as something very different, and I'm probably going to look at it from this perspective right there, which is the system perspective. If I'm the guy who's putting the weapons on that aircraft, I'm probably not looking at it from this perspective. I'm probably looking at it from that perspective, right? I'm probably looking at it from more of a weapon system perspective. If I'm the person who's doing the analysis, maybe I'm an operations research analyst, and I'm doing some modeling and simulation. I'm trying to figure out what the performance is. Maybe that's what my aircraft looks like, right? If I'm a member of Congress, that aircraft may look like jobs in my district or jobs in my state. And if I'm the comptroller, that aircraft may look like dollar signs. So one aircraft, but different people are able to view this the same way. So we have to have a way to represent this one system numerous ways so we can look at it from a lot of different perspectives and have all these things related to actually get to the true model-based system engineering environment. So one of the things we need structure, right? So structure defines relationships between the system entities, right? And this helps to establish concordance. So on the left, the picture on the left is shipbuilding, right? So the shipbuilding doesn't only consist of the individual building blocks, but it involves how to bring those building blocks together to form a functional entity. So we have to define structure, and we often define structure with some sort of conceptual data model, maybe a schema. A lot of languages, a lot of tools have a schema that you can follow. So when we're looking at structure, we also have to consider languages, because what helps us build that structure, what builds those defines those relationships within that structure is your ontology that's built into your modeling language. So the modeling language helps us to develop the system model, and there's a couple ways of doing these modeling languages, right? One could be that I'm just looking at things from a visual perspective, right? I'm looking at what I call a visual representation or a logical construct, right? The second way is I just have an ontology. I'm able to see the definitions of things. And the third way is to have a visual construct and an ontology. So when I talk about ontology, I'm talking about the standardized definition of terms and concepts and the relationships between the two. I not only have to understand what the entity is, but I have to understand how that entity is related to another entity. Because if I'm looking at an operation, for example, I may say, what capability does this operation satisfy? Right? So I should be able to link back to some sort of capability, right? I should be able to also say, how does what system element performs that operation? I should have the link to that. So when I look at a model-based system engineering world, each entity is only represented one time, but has traceability across the entire system, right? And I could extend this out to more traditional systems engineering and program management, things like scheduling or risk or cost, maybe even performance, maybe even reliability. So that's when we talk about modeling languages. I think modeling languages are key. I think we give a lot of lip service to like Sysml or UML, but really the modeling languages are key. So we talk about ontology. I said there's an ontology perspective. When I talk about ontology, I think about the DODEF Meta Model 2.0, right? So the DODEF Meta Model 2.0 is it's a great list of terms, and that great list of terms, helps us to define a lot of things that are being used within DoD. However, there's no visualization models that go along with it. So you may say, well, wait a minute, what about all those 52 different models in DODEF? Okay, so I would say that the DM2 informs that, but the DM2 does not prescribe that, right? So I think this is an ontology only. Well, I think it's pretty complete The problem is that it has almost 600 entries. And I'm not sure about you, but I would have a hard time tracking those 600 entries. And if I was trying to use that as an ontology to build the relationships between things, I'm going to get lost in the details pretty quick, right? So that's what we mean by an ontology-based language. It's only the DODF Meta Model 2.0. Look at Sysml, the system modeling language. The system modeling language is a visualization modeling language. It has a very limited ontology behind it. Very limited. It shows how things are supposed to be connected. It gives that little bit of a definition for you to build those diagrams. But there's not really a true ontology, which details the different core entities or primary entities, nor does it specify any relationship between those entities, right? So Sysml was developed by a joint effort between the Object Management Group and COSI about 15 years ago. And today it can, so the way they did it was they took UML, the Unified Modeling Language, which is used by programmers and software people, and they said, hey, we need some of that. Worked pretty well for those software guys. So UML has 14 different models, and when in COSI and OMG and the developers of Sysml developed that, they said, well, we don't need all 14 of those. We only need 7. So they took 7 of those models from UML and adopted them to Sysml. Then they said, well, wait a minute, we have two other diagram types that are needed, and that's a requirements diagram and a parametrics diagram. These are things that we need as systems engineers, but we don't necessarily need those things as the software people don't need those. So that's what it is today. Basically 4 thematic areas: behaviors, requirements, structure, and parametrics, right? There's four what Sysml will call the 4 pillars. And within that, there's 9 different diagrams. Sysml, the Sysml 2.0 request for proposals is on the street, and with that proposal, they're specifying the number of pillars is going to be expanded from 4 to 8, adding a few others. They don't say how many new diagrams are going to be in there, right? But I would estimate that maybe the diagrams would double, maybe. So I'm thinking somewhere 18 to 20-ish diagrams, but that's just a guess on my part. I have no insight into any of that. They have a modeling language that does both, and it has an ontology, and it has a visual representation. That's a lifecycle modeling language. So presuming that you're here, you must have heard about the lifecycle modeling language. I'm not sure how you would have gotten into this webinar without it. I think that's a price of admission. But LML was designed as a language that goes across all the lifecycle disciplines to include the architecture, the design engineering, the test, the program management, and it's all into one framework. If you go back to Sysml for a moment, Sysml is just the design stuff, and I would argue it's the design stuff in the early phases of your system engineering life cycle. It does not include everything. So what this LML does, it has these visualization models with an ontology that has a common vocabulary and the relationships between those different entities that are defined within an ontology. So ontology is actually pretty simple and has 12 primary entities. Helps simplify that. I can even handle 12 different primary entities, and it has 8 different child entities at this point. And I can handle that, right? So now I'm looking at 20 different things and how those 20 different things are related, and I'm able to define my system. I'm able to define my system with that. So with each one of these entities that's defined, there's one or more LML models that apply to that. So, for example, if I want to see how I'm going to model an action entity, I could use the action diagram, which is sort of like a functional flow block diagram or enhanced functional flow block diagram, or if you speak Sysml, maybe it's like an asset diagram. However, the action diagram is unique. So we have these different LML entities in there. We also, now you may say, Warren, wait a minute, this doesn't make sense. You already said that one of the problems in system engineering is that we have a difficult time handling complexity. Now, how are you going to handle that complexity with only 20 different entities, essentially, when you look at all the primary and secondary? Well, the complexity is really in the relationships between the entities, right? And the relationships between the entities are shown at the basic level on the left-hand side. You can see how things flow. You can see, we get some sort of artifact that maybe describes the work we want to do. We have some sort of statement which leads to, say, some sort of high-level requirements potentially, or maybe in DoD's perspective, we're looking at a list of capabilities. We have some sort of, we're able to go through the modeling process. We're able to have some sort of action. That action has different inputs and outputs with it. Performing that action is an asset or some sort of system element, right? Within those system elements are connected through a series of interfaces or connections. And those system elements have some sort of characteristics or measures, and those characteristics could be cost, could be schedule, could be performance, could be a lot of different things. So that's a basic level right there. But when you look at more detailed level within that matrix, you say, well, it's just a matrix. That matrix has relationships between those two that are pretty complex. I couldn't imagine having a 600 by 600 matrix that I have to now deal with the relationships between there. So my argument here is that the ontology should be kept simple. So I know Sysml 2.0, they're seeking an ontology. That's fine, but keep it simple. If you look at system engineering as a whole, system engineering as a whole does not have a lot of fundamental terms. In fact, you look at it across system engineering, and it becomes a problem sometimes because we have a definition of one thing, right? Or we have one term and we could have 5 or 6 definitions from it. I think if systems engineering as a whole and model-based system engineering in particular is going to expand, we have to have what I would call fundamental truths, and these fundamental truths are these different things that we're trying to have. So other disciplines have a fundamental truth. Why shouldn't we have our fundamental truth? So some of you say, well, now I'm confused. I'm confused because some people are talking about Sysml, some people are talking about LML, some people even talk about UML. Some people, they go back and forth, and when they're talking about Sysml, they're talking, they just go back and forth between Sysml and UML, and say, well, what is this? Are they really doing the same thing? So when you think about Sysml and LML, right? Sysml and LML, they're trying to solve the same problem. Both are trying to address designing the system, right? That's what they're trying to do. So we already said that I can link the LML entities and the LML models. Okay, I already said to do that. I can do that, right? I showed that 2 charts ago. I already said, so I haven't said that now I can take these LML models and I can link each one of these LML models to different Sysml diagrams. Okay, and oh, by the way, there's more LML diagrams or models than there are Sysml diagrams at this point, right? But I can link that. So now if I can link the Sysml diagrams to LML models, and I can link the LML models to the LML entities. I can link the Sysml diagrams to the LML entities, and this would give the Sysml 2.0 groups that are working on that would give them a good place to start with their ontology. Just personal opinion. See, you guys didn't think you were coming here and hear my personal opinions. Then you have modeling processes. I don't care what your modeling processes are. You know, the modeling processes could be or going to differ from organization to organization, right? Maybe within the organizations you're going to have different modeling processes, and these modeling processes could be your architecture processes or your analysis processes, or when I say analysis process, I mean your dynamic process, which will include simulation, and it could include other things such as risk analysis, programmatic stuff, cost and schedule things. When I talk about the analytical methods, it could be discrete event simulation. It could be system dynamics modeling. But those are what I consider modeling processes. And hopefully, when you're working with your modeling processes, you're using the best process to address the problem at hand. So, what I like to develop my static architecture. I like to, from an architectural perspective, I like to draw things out. I like to diagram things out. Hopefully, in some sort of tool where I'm able to have some sort of ontology that helps me to make the relationships within the system that I need to make. So with this, I developed my static architecture. Okay, now I could draw anything. I could draw that elephants can fly, right? And but it really can't fly because probably ears aren't big enough or whatever, or ears aren't strong enough to make them fly. So I could draw anything. But what really happens when I'm taking it into an environment where that system has to perform, right? So what I take those static models, I bring those static models into some sort of simulation world. You could do it outside the tool if you want. You can use multiple tools. I've done that. Or you can use a single tool. Interslate has a very good simulator that allows me to do dynamic discrete event simulation and Monte Carlo simulation. So it's a really good simulator. So now I could bring that into this dynamic world. And what I like to do, I like to put what I call a heavy load on that system. And that I may put a load on that system. I may put, when I say a load, I mean requirements going into that system that are going to severely stress the system. I don't care how my system performs on an average day, because I'm not building my system for an average day. I'm building my system for a not so great day, right? So I want to see how my system is going to perform. So I bring it into the simulation process, and what I like to do, I like to stress the system until I break it. And once I break it, I know how to fix it. I know what has to be fixed, and I go over there and I can update my architecture. If I do that, then I have a cost associated with that, right? And I could go to my boss at that point, or I could go to the decision maker and say, hey, decision maker, I just broke your system. And decision maker, and this is how much it's going to cost to fix it. And decision maker is going to say, a couple things, right? Probably going to ask me, what the likelihood of occurrence is going to be of that heavy load I put on my simulation. You put this heavy requirements on the system. What's the likelihood of that happening? I don't know. Maybe if I'm doing some sort of imagery collection from, say, a satellite, maybe I'm looking at collecting things that I just do on a daily basis, which maybe I'll call the piece backdrop. Maybe I'll have a couple different theaters of war that are going on, and maybe I'll have some sort of other contingency like a hurricane or something like that that I have to take imagery for, right? That's what I'll consider a heavy load, right? So the question may be, what is the likelihood of that occurring? And I may say, well, boss, it's the likelihood's 5%, but it's going to cost you a ton of money. Decision makers may say, well, I'll take that risk. We're not going to spend the money. But what if I said that was 90% and it's still going to cost a ton of money? Well, I think the decision maker is going to have a different thought. The decision maker is going to have to find a way to go back and get more money, have a bake sale, whatever they do to get money, right? So that's when I look at a model-based system engineering environment, I'm able to do that, and with InnoSlate, I'm able to do it within one tool set. If I was using something else, I could certainly do it. But when you think about if I have a different tool for architecture and different tool for modeling and simulation, when you think about the single source of technical truth and building that ontology and building those elements or entities within that ontology, everything's going to have to work towards that same ontology, or you're going to have a translator to translate from one ontology or one set of definitions and relationships to another to make this work. Either way, it could work, and we're just working with one. We're looking at the system and we're training the system, just like we would a real system. We're looking at just with each entity being represented one time, we hope. So now I've done all this work. I don't necessarily want to show seniors all this stuff in the tool. The seniors aren't going to want to see this stuff in the tool, right? They're going to want to see things in say a format that they can understand. And maybe we call that format a presentation framework, right? I call it a presentation framework. And what the presentation framework does, it provides a framework for all logical constructs and visualization models that could be used for a particular stakeholder. So there's a couple different examples of what I would consider a presentation framework. I would consider the Department of Defense Architecture Framework as a presentation framework, as well as the Zachman framework, as well as the emerging Unified Architecture Framework. Those are all frameworks, and they provide a good base of different visualizations where the stakeholder can see things in their own terms, right? So that's an important thing. The stakeholder has to see things in their own terms. So for those of you who are developing Sysml diagrams, and I've heard recently that, hey, we could cancel all DODAF if we just did things with Sysml diagrams. So that means that you're limiting the way the stakeholder can see the information that they're going to need to make decisions to 9 different perspectives, right? We look at DODAF. DODAF has 8 different viewpoints containing 52 different models. It's expanded recently. Well, expanded. I guess when I say recently, it seems like yesterday, but it was really 2009 when it went from 4 different viewpoints containing 26 models to 52 different viewpoints. So it's just this provides the guidance and the rules of. I like it because it provides a nice binning of my different individual views within certain viewpoints. So I kind of like that. So if I want to do things from an operational perspective, all those different views are listed there. So I view this as part of model-based system engineering, and this is part of model-based system engineering that is really the way we communicate our system design to the stakeholder. Because the stakeholder is presumably knowledgeable of this, whatever framework they want. They probably aren't knowledgeable about the inner workings of a particular model, right? And they'll probably be uncomfortable seeing the inner workings of a particular model. That's really more for the engineers to work on their work products. So when we look at model-based system engineering, it's more than system architecting, right? Model-based system engineering includes programmatic stuff, includes the architecture stuff, but also includes the programmatic stuff, the risk, the schedule, the cost, includes the requirements, right? So my system there, which grew from being a cube to whatever you call this particular shape, you know, that system is going to have some sort of requirements along with it. It's also going to have some sort of physical thing. So here it's more of a conceptual thing. Well, what does that, you know, what's the physical part? What does it look like from a system perspective, whether conceptual or physical, right? Also has some sort of measures to it, has some sort of parametrics to it. It shows what my performance is. It shows if my system goes from, when I say, does my architecture close? Does my system go from point A to point Z without breaking? And does it do so within a timeliness perspective? And I foresee the future that, at least I hope in the future, we're going to be able to see this linked to a computer-aided design. If we could do that, then we could go from all the way from those upfront needs, or whatever you want to call those in DoD terms, or their capabilities. Maybe some people still call them the big R and little R requirements, so refer to the big R, the high-level requirements. You know, it goes from there all the way down to requirements generation, analysis, all the way into your computer-aided design, right? And if you have this in one environment, then from a computer-aided design perspective, I can design down to the part level. If I could design down to the part level, then guess what I could do? I could do some sort of 3D printing probably with that part level. So now I have one environment. I'm not saying one tool, and I'm not saying one database. I'm saying one environment where I could do all that. Because what happens today, we do all this system engineering stuff up front, and then we get to the end, and we take all this stuff and we throw it over the bulkhead to design engineers. And I don't know, design engineers use stuff we're developing. We spend a lot of money developing this stuff. We spend a lot of time doing the analysis. Where's that linkage between what the architecture and the system engineering products are done and models are done up front? Where's that linkage to the computer-aided design after the design engineers get it? So some may say, how come you didn't talk about model-based system engineering tools? I view model-based system engineering tools as being at the intersection of those four tenets of model-based system engineering. I hear a lot of people, they come to me and they say, we want to do this model-based system engineering. We want to start model-based system engineering in our organization. What tools should we use? You know, we need to have a tool study immediately. And okay, so you have some sort of preconceived notion of your modeling language. What kind of structure do you have? What kind of processes do you envision having? How do you want to see that output of your model? You know, from a presentation framework perspective. From there, those are four questions that I would start with while I'm doing a tool study. So I don't talk about tools. I work for the government. I'm not a tool salesperson. I have my favorites, but I'm not a salesperson. So here's just a few of them. So but the tools are really in the center. So I tried to keep this model-based system engineering discussion away from the tools because we all often seem comfortable going towards the tools. So what's the benefits of model-based system engineering? One, it's going to help us ensure that we focus on the vision. It's going to ensure that we have our stakeholder needs are clearly understood and prioritized and addressed. It's going to help us manage complexity. Probably the largest benefits in model-based system engineering and a true model-based system engineering world is to manage complexity. Hopefully we're using this stuff that we're developing our architectures and this other stuff to make engineering decisions. I know a lot of organizations, they say they have to develop an architecture because the policy says we have to develop architecture. What do? They go on and they hire their favorite contractor. They develop that architecture. It goes through some sort of systems engineering technical review. They get the check mark and it goes on the shelf, right? So if you're going to have a model-based system engineering world, first of all, stuff's not, creating this environment is not cheap and it's very time-consuming. You're going to have to change the way you do business. And you're going to have to keep that model updated. And if you're going to do all that, you should use it to support engineering decisions and manage change and identify critical gaps and special items for consideration. Model-based system engineering is not a replacement for system engineering. So some people say, well, once we have model-based system engineering, all these system engineers can go away. I would argue that model-based system engineering is an enabler toward to doing system engineering better. I know while I was a chief architect, you know, sometimes I would have the analysts do stuff or the engineers that work for me do stuff, and it would take them forever to do it, right? And you know, so I wanted them to go to a model-based world and facilitate going to a model-based world, so that they're able to look at more alternatives, and we're able to do more things as a systems engineer instead of just somebody who's trying to input data. So with that being said, I really appreciate your time today. You know, my contact info is on the title slide. Feel free to reach out. I really appreciate your time. And with that, I'll turn it over to you, Elizabeth. Thank you.
Thanks, Warren. We've already received several questions. If you haven't had a chance to do so, use the panel on the right to ask us questions, and we'll get to as many as we can. So our first question is, if Navy perspective, then what percentage of CPOs do you have aboard?
Can you repeat that, please?
Of course. Our question is, it's from the very beginning. If Navy perspective, then what percentage of CPOs do you have aboard?
I don't know the answer to that question.
All right, we'll move on to another question then. This is more of a comment. MBSE was used in 1991 for SDI using RDD 100. The difference was the ability to model behavior as well as context and structure. Our next question is a system model a necessary, sufficient, and efficient ontology of a problem suppression system?
I'll look at the question. So I would argue that that the ontology should represent the system, and if you have an ontology that represents a system, you'd be able to model the system sufficiently and efficiently. And I would argue if you're going to have an ontology, so ontology, I think in the future is going to have to become a big. I think it's going to have to become a big topic within model-based system engineering and system engineering as a whole. I think if you're going to have an ontology, it's going to have to be an efficient ontology, which means you're going to have the fewer the entities, the better. So I hope that answers the question, or at least addresses the question.
Thanks, Warren. Our next question is, how does Universal Architecture Framework fit into your tutorial on the aspects of MBSE?
So I would say that UAF is another framework, as the title says. So I would say UAF is a presentation framework. So I mean, if you want to see things from a UAF perspective, that's the type of presentation framework that you'll be looking for in a tool. And UAF is a pretty good way to bin things, just like DORF is a good way to bin things. So I think it's UAF definitely falls within the presentation framework perspective.
We have a question from slide 22. Are you examining the system or only your model of the system, including the bugs in your model and simulator?
So hopefully what I've done, hopefully I have captured a virtual representation of my system in my model. So I'm not just looking at my model, but I'm trying to, hopefully I'm looking at a virtual representation of my system so I can examine my system and the performance and the bugs and all that stuff and hopefully catch the bugs before it actually goes to some sort of production. So in here, what I'm looking at, I'm developed my system. I have this virtual representation of my system from a static perspective. Now I want to see if that's just going to work, right? And I look from there. I do some sort of simulation, and I'm able to figure out if my system works. Now, given the constraints, keep in mind this is a laboratory environment. The real world environment doesn't, it's only modeled sufficiently where I can answer the questions. It doesn't involve all the different aspects of my system. But I think by doing it this way, I think it's better than a lot of our system engineering and model-based system engineering process we have today.
Thank you. Our next question is, does Zachman framework have an ontology or data model like the DM2 or the UKM3 model?
Not that I know of. From the Zachman framework, they have, it looks like they have the different stakeholders, they have the different data types. Within each one of those cells, you have a different model prescribed, but as far as I know, the Zachman framework only goes down to the actual model type or diagram type. It doesn't. Ontology goes further than the diagram type and the model type. The ontology actually addresses how these things are going to work within the system. And if you have that ontology, you're able to represent that virtual system. I think the Zachman framework doesn't do that. However, if I want to represent something as a hierarchy diagram, for example, the Zachman framework has some hierarchy diagrams. I could export that to, whatever, so that the stakeholder can see things in their terms if they prefer to use the Zachman framework.
Thank you. Our next question is from slide 26. Are you saying these facilitate model-based systems engineering?
So I would say, yes, I would say they facilitate model-based system engineering. And I would also say that so Steve's standing right here next to me, so Steve's going to take out the knives on this one, right? But I think if you're going to look at, if you're going to try to select the tool that's best for your organization, you're going to need to answer these questions in these four areas at very least. And the model-based system engineering tools is what allows me to develop my system in the virtual world using the modeling language, whatever that, or the structure, however that's defined, the model-based processes I'm going to use. And given that I have to have something, I'm just not doing this for me. I'm doing it for stakeholders. So the stakeholder needs to have some sort of reference to make the decision, which is the presentation.
Thanks, Warren. Our next question is, should we consider other popular tools like TOGAF-based Orbis tools, Sparks EA, etc.?
Yeah, I'm not sure all those are tools, right? Yeah, I mean, TOGAF I think is a framework. Should we consider TOGAF? Well, I consider TOGAF as being part of the presentation frameworks. I'm not. Again, I work for the Department of the Navy, so I don't advocate any tool. I certainly have my favorite, but I don't advocate any particular tool. So I would argue that any tools out there today or any tools out there that are going to emerge in the future should be under consideration to help us as system engineers do our job better.
Thank you, Warren. Our next question is, from your experience, what are some programs that are exemplars in applying MBSE, either Navy, other DoD, or commercial?
You know, I ask that question all the time. I get an answer to that question all the time. I think right now with model-based system engineering, I think it's really the Wild West. I mean, we've been trying to transform from when I say we, I mean the system engineering community as a whole has been trying to transform from a traditional system engineering world to a model-based world for the last 15 years. I would argue during part of those years it didn't get much traction, especially much traction within DoD. And today I think it's a Wild West, and I think it's a Wild West because there's early definitions that help us define exactly what model-based system engineering is. So you look at a lot of programs today, they're using Sysml, for example, with Magic Draw, and you know, are they successful? I guess they're getting it out of it they're getting out of it what they're asking for the simulation to do, or for the model-based system engineering tool to do in that environment. I would argue they're not getting out of it a true virtual representation of the system. They're essentially getting out of it a series of essentially what could be hard copy diagrams that they're going to have to correlate. However, with that being said, the capability to represent your system exists virtually today in several tools. And there's some ontologies out there, like the Lifecycle Model language, that is good for that. So plug for the Lifecycle Model language. Lifecycle Model language is an open standard. So if you wanted to develop your own tool using Lifecycle Model language, hey, go to our website and download the spec, and it's a good place to start if that's what you want to do.
Thank you, Warren. Our next question is from slide 25. Could a functional architecture diagram be added?
So yeah, so a functional architecture diagram certainly could be added. You know, basically any dimension that I could think of within a system should be included here. But I guess when it comes to being a PowerPoint ranger, I guess I run out of space. I'm not very creative.
Thanks, Warren. We're going to skip ahead a couple questions because we have another question from slide 25. Today, CAD-K and the notion of digital twin seems to be systems engineering MBSE of the 21st century. The link to the virtual simulated model to the physical product is much more integrated today. Do you see this affecting the MBSE methodology?
I would see it affecting the MBSE methodology, but more in a positive way. So when I look at, so for example, you look at the design of the newest Navy's newest aircraft carrier, the General Ford. A lot of that was done with 3D modeling. However, not everything could be done with 3D modeling. There has to be some early, I think there has to be some sort of early system engineering work that has to be done, and that's a lot of what model-based system engineering tools capture today. However, I mean, the faster we get to the models, the faster we get to actually having a virtual representation of the system, being able to capture not only the physical and the functional perspective, but all the different attributes of risk and the cost, performance, and all that stuff. I think the sooner we get there and have one environment, like I tried to show on the slide, the better it will be.
Thank you, Warren. Our next question is, what are your thoughts on maintaining a digital twin throughout the life cycle?
I think if we're going to use model-based system engineering, and I think model-based system engineering has to be an enabler for system engineering as a whole, not just the upfront part of what I call the upper left-hand side of the system engineering B. I think the digital twin is essential because we're able to make adjustments to our system, make changes make changes to our system throughout the life cycle and make decisions based on that model. Now the trick is there's a couple things that maybe our senior leaders don't like to hear. One of the things is that the model's never done. I mean, it's a continual process. It's constantly being upgraded. What they don't understand is we start talking about model-based system engineering. It's really going to if it's going to be successful, it's going to have to force a change in the work culture of your organization, how you fundamentally do system engineering. It's not saying everybody has to be proficient on some sort of model-based system engineering tool, but you have to go away from thinking from a thing in from your system as a document or a diagram into actually thinking of the virtual representation of the system.
Thank you, Warren. Our next question is, to what degree should the system's ontology be specific to the domain? Would it be preferential to use a generic ontology, such as the one built in L UML? Or should a generic ontology be extended to some degree to meet domain-specific ideas? If the latter, what is your cutoff for when to generate a new entity or extend an existing one versus only using the existing entities in the ontology?
So I think there has to be some sort of fundamental truths to system engineering, and those fundamental truths, I believe, would be included in ontology. So, for example, just say that the LML ontology was the fundamental truth. So the LML ontology is, it captures a lot of stuff, but if you want something that's domain specific, you could certainly add to that ontology for your own domain, right? And there's nothing saying you can't do that. There's nothing saying you can't add different diagrams that you represent within your own domain. But at the core, the fundamentals are the same, whether you call some sort of operation action or not. I mean, you can call that whatever you want, but every system has some fundamental truths. They have actions. They have assets. They have has risk, has cost, things like that. So, yeah, I think you could. I think it would be beneficial if you extend it to your domain, but keep in the current a common base across system engineering.
Thanks, Warren. Just to clarify, aren't the DODAF, MODAF, and UAF both presentation frameworks and ontologies/data models?
I would say they're more presentation frameworks. I think DODAF has a meta model 2.0, but the DODAF meta model 2.0, you could develop the presentation frameworks or the different views within DODAF without knowing anything about the DODAF meta model 2.0. You could use the DODAF meta model 2.0 without using the DODAF views. So I would say that DODAF, MODAF, and UAF are presentation frameworks. I'm not sure I would classify them all as ontologies, especially since they don't necessarily specify how the different entities are that's contained within an overlay.
Thanks, Warren. We have time for just a few more questions. Our next question is, why are the terms in the ontologies different from those in systems engineering standards? Why are DODAF terms different from ISO, IEC, IEEE 15288 terms?
I think that's because it's DoD. For some reason, DoD wants to do their own thing. I think they're trying to get better at linking back to those other standard terms, but I think for the most part, I think DoD's trying to. Yeah, and a lot of times you have to remember DODAF goes back to 1996. So with the C4ISR architecture framework, that probably does predate 15 to.
Thanks, Warren. Our next question is, On a related note, is there any advantages to building separate ontological structures that could be considered levels of abstraction? There's always seems to be a lot of discussion of systems versus subsystems versus component that distract from system development. I believe LML solves this by abstracting the physical entity as an asset without distinction of the layer of abstraction.
That is true. LML does not, but what you so when we went back to that diagram where I showed up front where it was the cube, the second thing I showed was the height, right? So the height represents decomposition. So so in a true model-based system engineering world, you have the top level represented, then you could decompose to the next level. And if you want to roll that back up, you could roll that back up. So from the LML perspective, an asset is an asset regardless if that asset is at the system level or if it's all the way down at the part level. Now we could claim things are system, subsystems, assemblies, components, all the way down to the part level, for example. But basically all assets, because why we're trying to, on the LML perspective, they're trying to keep the language as simple as possible, and hopefully get into those what we'll call the fundamental truths of system engineering.
Thanks, Warren. The second part to that question is, finally, has any established organizations, preferably in the DoD, provided a good framework for transitioning to MBSE from document-based systems engineering from a management standpoint? It seems many organizations simply say MBSE go without laying adequate groundwork in making the transition.
So there's one organization, which I will not mention, but one organization in the Department of the Navy that it seems to me that they're relying on the Big Bang Theory, right? So have this grand plan, and one day they're going to flip the switch, and boom, the world's going to change. I think this is an area that needs to be explored further. You're right. We do say model-based system engineering go, and that's a problem. I think I personally think that starting out smaller rather than larger, proving the concept, and being able to expand on that concept for your organization is better than doing what the one Navy organization is doing from a Big Bang Theory perspective. So, hope that answers the question.
Thanks, Warren.
There has to be an adequate transition plan, right? And that transition plan can't be a miracle occurs tonight and tomorrow we're all going to be model-based system engineers.
Absolutely. Thank you. Just a couple more questions. The last CVA I visited had greater than 80 unimplemented mod kits, one 8-month-old. Does your digital twin show the state?
I don't know. I imagine it could, but I haven't thought of it from that perspective.
We also have another question for this page on slide 25. Does digital twin belong here?
I'll claim that this environment represents the digital twin.
Thanks, Warren. We have one last question. Are you familiar with UPDM and its efforts with DODAF, MODAF, and UAF?
I am somewhat familiar with those efforts, yes. So some people say that DODAF and MODAF are going to be part of the unified architecture framework. I think at this point, I think there's too much uncertainty. I heard somebody, rather senior person in DoD, say, well, if we could do everything with Sysml and with those 9 miles in Sysml, we should just cancel DODAF. I think there's a lot of uncertainty there. I think it's still yet to be proven how the unified architecture framework is going to include DODAF and MODAF along with the NATO framework. Is that going to be suitable to those of us in the U.S.? especially within a DoD. I don't know.
Thank you, Warren. I'm afraid that's all we have time for today. If you still have questions, please reach out to us after the webinar. If we do not get to any of your questions, we'll contact you. We would like to thank you again for joining us today. As a reminder, we'll be following up with you very soon to send you a link to the recording and the presentation slide deck. We also encourage you to visit our website as well as connect with us on social media. That concludes today's presentation. Thank you again for your attendance, and we hope to see you again at our next webinar. Please enjoy the rest of your day.